Thank you. And thank you for giving me this kind of opportunity. So note that this title is about the Calabi, not about the Calabi function, but Calabi type function. They had some meaning. And in this talk, we're interested in the Fano manifolds and some scalar metrics in the first chain class here, and fixed this convergent class, and then any such metric can be written by some, as you know, some scalar potential function phi, which I wrote here. If we fixed some reference metric omega 0, like this, that's throughout this talk I fixed this notation. And our starting point is the result of Chandra-Sassoon, which state that this Fano manifold has Kerr-Einstein metric, so it's Kerr-Einstein metric, if and only if the manifold is k-polystable. So yeah, it looks completed the problem, but in fact, only a few Fano manifolds admit such a standard metric. For example, let me see. Yep. So for example, the row up of P2 at some point does not have a. It's known that this surface does not have any Kerr-Einstein metric. But for this easy example, we know that there exists some extension, some generalization. For example, Kerr is certain. But in higher dimension, there are a lot of other example, like deformation of the Mukai-Umemura threefold, which not have any kind of such standard Kerr metric. This is an example of K semi-stable variety that for example, if you have the blow-up of quadratic fivefold, then there is example of K. Sorry. So these in the higher dimension there as well exist K unstable manifolds, and of course it doesn't have any kind of standard measure like Kerr-Einstein or Kerr is certain. I ran it from Dalcroix's paper. Okay, but there are such a lot of kind of examples. So in this today, our main question is that then how can we say about the general Fano manifolds abstractly? How far is X from Kerr-Einstein condition? That's the topic of this talk. So let me to go further. Let me go first fix some notations. So let me write the Ricci curvature of this given metric, like here, and consider the difference of Ricci curvature with the metric omega. Then by DD lemma, we can take the Ricci potential rho, and we always normalize the Ricci potential to so that the integration of e to o minus 1 is 0. This is the normalizing condition which we take throughout this talk. And then we consider the integration of square of e to o minus 1, this guy, and study about the infimum of this functional over any over all calorimetrics. So this is as I explained above. This is represented by some scalar potential function phi. So phi always represents omega, which is omega phi. This functional so the square integration of the square of e to o minus 1 is simply the analog of the Calabi functional, which was originally defined in terms of the scalar curvature. But we are now consider the difference is that we consider the Ricci potential. So that we can only say about the Fano manifolds. And to study the lower bound of this functional, the first point is that it's actually convenient to consider the restriction of things to each direction on the space of scalar potentials. So the direction means that we consider the specific lay or all lays in the space of calorimetrics, which I denote phi. And we're particularly interested in the case t goes to infinity and the behavior of these functionals. And first, by using Cauchy-Schwarz inequality, we have that the integration of phi dot against e to rho minus 1 is controlled by the Calabi functional times some norm of the tangent vector of this lay. So the Calabi functional, what we are interested in, is bounded from below by some integration of phi dot times e to rho minus 1. And there exists actually there exists a canonical functional d, which usually denoted by d phi, which is functional over the space of scalar potentials and characterized by the property that the differential of d is precisely equals to integration of phi dot against e to rho minus 1. So this is almost a definition of d functional. Of course, there exists a precise concrete definition of d functional, like so I wrote a precise definition in the below, but we don't need this precise definition today. So the most important property is that the differential of d is given by the phi dot times. So that's like evaluate the e to rho minus 1 along any direction phi dot. And the second point is that this slope, particularly the slope at infinity of the given lay, it can be translated into the words of algebraic geometry. So that's the second point I will explain. So if one takes a test configuration, that's there's a flat family over the complex line endowed with some Taylor section, which makes everything equivariant. And the family is about of given Fano manifold with anti-canonical polarization. So the generic fiber is, in particular, using C-star action, using Taylor section, isomorphic to the simple product space of X with line. And if we take a test configuration, if we take such test configuration and any positively curved fiber metric on this line bundle on this family, which was given as a datum, then the metric, fiber metric, defines some function on the product space. So we use this identification via the Taylor section, and the metric was identified with some smooth weight function on the product space, such that the d-var of phi is positive. And this function, by changing variables, defines the lay on the space of scalar potentials in the way that the t goes to infinity as the parameter of the complex line goes to the origin. So the fiber of the family goes to 0 as t goes to infinity. That's the rule. So the test configuration with some metric data gives the lay. So the choice, it doesn't matter. So the choice of the fiber metric doesn't matter because if you have some two metric phi and say c, then the difference of these two guys can be abounded uniformly in T. So the behavior of those functionals in if you take T goes, if you take T large, then the behavior of those functionals are independent of the choice of such fiber metrics. And the second remark I like to give here is that the lay phi t is geodesic if and only if the big phi satisfies the degenerate Monge-Ampere equation. So this is unique for the prescribed boundary condition. So sometimes it's very convenient to take this sort of canonical ray attached to each test configuration. So in particular, geodesic is canonically attached to each test configuration. And then theorem of Robert Berman says that our interest, the slope of the D functional along such associated ray, this one, is given by some degree of the line bundle and the intersection number of line bundles line bundle L for the family and the canonical divisor of the compactified family. So this X bar denote the natural compactification of this of the above test configuration equivalent family. And this pi is a push down to the parameter space. So the slope is given by some numerical invariant, which we denote d of xl. This we call this as d invariant, and the right. So the existence of Kerr-Einstein metric, for example, corresponds to the positivity of these D invariants for test configurations. Because if this D invariant is positive, then the slope, any slope at any along any geodesic is positive. So we can expect that the D energy, D functional, is properly closed. Is properly closed. So which then we can expect. We can also expect that the energy functional has the critical point. There's a story for showing the existence of Kerr-Einstein. One story for showing the existence of Kerr-Einstein metric. And no, I also noticed that if you consider the scalar curvature set, if you also consider the scalar curvature setting, then the functional is replaced with the more famous K energy functional. And the right-hand side in this formula is precisely the Donaldson-Futaki invariant. But in the Fano case, we have the other D invariant like this. And this D invariant, it's more subtle point, but the D is not precisely equivalent to Donaldson-Futaki invariant. But the positivity of D condition for all test configuration is eventually equivalent to the K stability condition. In many points, the D functional and D invariant formulation is easier to handle with. So, for example, in my talk, this Ricci potential setting works well. Okay, and let me go back to the key inequality, only the Cauchy-Schwarz inequality. But so we first observe that the Calabi functional is bounded from below by the D with norm. The D functional, slope of the D functional divided by some norm of the tangent vector. And also the norm, like invariants, can be described as follows. So it is given by the limit of some spectral measure with respect to the torus action, induced torus action on to the space of global sections on the center fiber. So the torus acts on the spectral space, and then we have the weighted torus action lambda I, and consider the Dirac delta measure and take the limit. Then we get the norm. So the two guys are at the same time can be translated into the world of geometry. So we have some analog of Donaldson's famous lower bound inequality. So the looks like Calabi functional is bounded from below by the D invariant divided by some norm. This is the background, and our main theorem today is that this is actually the equality. So this solves a variant of Donaldson's conjecture in the scalar curvature setting, which state that the lower bound of the Calabi functional in terms of the scalar curvature is equivalent to the supremum of the minus of Donaldson-Futaki invariant. But as I will explain, the scalar curvature setting looks more difficult. And the original question for the Calabi functional has not yet completed. Has been not yet completed. But I can remark that in a similar technique, means and share, he shows for the original Calabi functional that this equality holds if we take phi a singular metric and also replace the test configuration with possibly transcendental ray phi t. So it's not a word of algebraic geometry, but if you replace the right-hand side some analytic corresponding quantity, then you have the equality. So that's the statement of the main result. So in the rest of the talk, I'd like to give some sketch of the proof. So, but do you have any questions so far?
If you can see the chat,
Yes.
Answer the question from Tevodros and Abraham. Would you consider moments for cubic power? I'm not sure what he precisely mean by this question, but you may.
Yeah, I'm not very sure about this question. Oh, there are another.
Yeah, question from Cheyenne Shu.
Our size of the question is about the whether the supremum is maximum or infimum is minimum. So yeah, that's I like to say. So for the right-hand side, the supremum is expected to maximum. We expect that this is maximum, but this infimum is never minimum. That this point would be cleared if he goes to go into proof, but our result does not say about the supremum is maximum. It is expected, but so if there exists some achievement of the supremum, then we could expect that there exists some canonical optimal destabilizing test configuration in the sense of D-invariant, but we don't know what it is. Thank you. Irrational. Yeah, so if you want to make the supremum to be maximum, then we should somehow extend the notion of test configuration, right? For example, we need to consider the irrational Tolas action. Yeah, but I can say about some special case. So, for example, the toric Fano manifolds. in the toric Fano manifolds, the case, the right-hand side is actually the maximum and attained by some convex function, but it is not it does not have rational coefficient in general. But there exists some irrational convex function which attains the supremum. Yeah, so it's a maximum. Yeah, so that's just the result. Oh, so sorry, I should say that's the result of the. So, sorry, I should.
I ask, did you say that even in toric case, the supremum of the right-hand side is
this is a result of
and maybe irrational?
Yes, yes.
I see. Thank you.
So this is so in the toric case, this is a result of Yao. That's the supremum is maximum. I should stress. So let's move to the sketch of the proof. So the first point is to introduce the gradient flow of the Ricci-Calabi type functional or Calabi type functional. So yeah, it's simply I simply here written down the gradient flow equation of the Calabi Ricci type Calabi function, and this is simply an analog of the famous Calabi flow. But as far as I know, this guy have not appeared in the literatures, and our first result, which is joint work with Tristan Collins and Ryosuke Takahashi, is there exists a long-time solution of this flow, and also converges to Kalan-Stein metric. And the proof is itself, I think, interesting because some routine strategy like C0 estimate using maximum principle is not effective in this case. So the sign of the linearization equation, linearized equation is bad, and we cannot simply apply maximum principle. And actually, we use some fact that blow up of this flow in finite time converges in some class of singular metrics. And then we use Kawoji's L-infinity estimate for the singular solution of the degenerate Monchampel equation. So this equation looks easier than Calabi flow, but still there are some up. Oh, sorry. Alexa, 止めて. So there are some technical matter for the proof. Anyway, we have a solution of this gradient flow. And changing the variables, we get some big phi on the product space. This is the flow translated into the function on the product space. This is the first point. And in the second step, we apply some variational methods developed by Berman, Dixon, Johnson, and Dervan-Székelyhidi, and many people, and many other people. So so we got phi here, and then we take some geodesic ray asymptotic to phi, because this phi on the product space is not pre-subharmonic function. So we need some geodesic asymptotic to phi, and this u. So let's denote the geodesic as u. then U is really the pre-subharmonic function on the product space, so that we may take the multiplier ideal sieve for any M. So this phi, of course, this phi and also the asymptotic geodesic ray U is very possibly very transcendental thing. But the multiplier sieve is by the result of Nadal. This is we know that this thing is a coherent ideal sieve, so we can take the blow up along this ideal to get some algebraic test configuration. So that's the sequence of test configuration which we can expect this guy could approximate the somehow the flow phi. And actually, at this stage, we can apply the result of Berman, Buxton, Johnson, and others here. So the sequence, the limit of the D-invariant of such constructed test configurations is bounded from below by the slope of first bounded from below by the slope of the D functional along a geodesic ray. This is precisely the result of one result of BBJ. And actually, this is we can understand that this is somehow the consequence of variant of Dumeli's approximation theorem. So this one can regard that this test configurations can be a sort of log of polynomials, and this one is PSH, approximate the pre-subharmonic functions should be approximated like that. And then the slope of D along geodesic is bounded from below by the flow, D along flow. This is simply a consequence of convexity. And again, by convexity, the slope of D along the flow is I'm sorry. So I think this one is not. This is equality, and this is for T. I'm sorry. So for any T, the slope of phi, slope of D at phi is equivalent to, by definition, minus of integration of phi dot against e to rho minus 1. And finally, this guy, the slope of D along the flow, is equivalent to the norm times the Calabi functional. This is exactly the consequence of the definition of the gradient flow. So in general, this is only an inequality of Cauchy-Schwarz, but because since we take the gradient flow of the Calabi functional, this one is desired. We have the desired inequality here. So this minus of D of the sequence of test coefficients is bigger than, not less than, the Calabi functional. That's the story of the proof. But of course, we have to a little more. We have to do a little more about the norm here. This is some analytic guy. So the final step is some comparison of norms that I omit this point today. So that I finished here the sketch of the proof. And in the end, add some remark about some another formulation using Kalalich flow. Yeah. Are there some questions?
I have a question in the chat.
Yeah, thank you. The flow always converges to some degenerate PSH metric. PSH metric on what space? Which space?
On the same space.
On the same space. I think it's not the case. So if there exists a Kerr-Einstein metric, the flow converges to Kerr-Einstein metric in the same space. But even in a toric case, the gradient of the Ricci type Calabi functional converges to some metric on the different space. It's not even the single polytope.
So did you say so you proved that the flow always converges to some another space, some metric on another space, or it is expected, just expected? Or
we're only expecting. We're only expecting. But even in a toric case, it looks very difficult because the polytope is separated into two parts.
Okay, so
geometrically we have two components on the central fiber.
The limit space is not irreducible.
Not irreducible.
I see. Thank you.
So the final remark is about another formulation. So by using the almost same argument, we can give a simple proof for the infimum, the equality, corresponding equality for the infimum of the entropy functional. So entropy functional is the integration of rho times E2O, this one, which some reduction of appears of some reduction of the of W-like functional, and for this functional, the infimum is equivalent to the supremum of some different H invariant introduced by Dervan-Székelyhidi. And they also proved equality holds using some deep result of Chanson 1 about the limit of Kalalich flow. But in our argument, we can use more pre-potential theoretic discussion, and so that, for example, we don't need a Gromov-Hausdorff conversion. So we use the Kalalich flow in place with the gradient flow of the Calabi functional. So the proof is, I think proof is more simple, but we cannot say about limit space in our argument. So that's really the advantage of the deep result of Chanson 1, I think. But I recently realized that our proof has some merit because we can also have the same result for even for singular X, thanks to the work of Santian about the Kalalich flow on the singular space. So the same kind of equality holds for singular Fano. So yeah, I think it's almost time. So I stop here. Thank you.